Brilliant. Thank you so much. So I want to talk about lower order statistics, right, that are still beyond 2 point, as I claim. And I think we can actually learn quite a lot from generally summary statistics, right? So even if we want to go to the map level, I think there are a lot of tests we can do. And today I want to give you a glimpse of why I think this is interesting. And also we were telling all of you to focus on challenges, right? So normally I advertise 1 point statistics and everyone should be like, this is amazing. But today I will actually also focus on challenges. And I really like Vienna because last time I came here, I had a serious problem with the bias model for our 1 point statistics. And then Jens solved all my problems. So now I will tell you about other problems I have. And maybe when I leave, then we will solve all of them. Right. So why do I like those 1 point statistics? So broadly speaking, right, we have our beautiful large scale structure. Of course, this is just a local one, but it's a nice full sky picture. And normally we do summary statistics, right? 2 point, 3 point, you name it. And what I don't like about endpoint correlation functions is that they average over all density environments, right? So if you want physical information, you might think, why not focus on different density environments, right? And the 1 point statistics are just a very simple way to actually do this. So what you can think, I basically now, on every location, I put a cell and I just count how many galaxies there are. Okay, maybe I accidentally, did I remove them? Or maybe that just doesn't work. Okay, there we go, right? So I have low number of galaxies, even more galaxies, and a very high number of galaxies. And roughly speaking, 1 point statistics means, right, I cover everything with lots of cells, and I compute a ratio of a cell of a given color, right, in the sense of how many tracers do I have in there, how large is my density, right, compared to all cells I put. And the cool thing is also that I think we are always in this regime, we want a very informative statistic, right? We want to learn cosmology, but in the end, we need to be able to predict the statistics, right, to compare to the observations. So in principle, I could imagine I find a very informative statistic, but I'm not able to like robustly predict it, right? Of course, simulations, right, are supposed to actually solve this problem and basically say, we can predict anything, right? So we then might as well use the most informative one. Right. So I want to briefly tell you why I believe those 1 point statistics where we basically do explicit smoothings and we implement a symmetry are nice. So a very simple argument is as follows. If I have statistics with an inbuilt symmetry, then this symmetry will translate into a simplified dynamics. And I just illustrated this here with a spherical cow. So all of those cells here have the same mean density, but they have different density distributions. And when I do histograms, right, or density splits, where I basically take all of the cells with the same mean density into like one bin, then essentially this corresponds to sort of stacking them. And if I have statistical isotropy, this will mean the average profile is spherical, right? So there's an inbuilt symmetry. And if you do proper math, you can actually see with a beautiful theory called large deviation statistics, you can then make an argument that the leading order dynamics will reflect this symmetry. And this is quite cool, so I won't focus on any of the details here. Just trust me, if you do this on dark matter density fields, this actually works quite nicely. So here we have the Quixote simulations. I fixed my scale. I said I like 10 megaparsec over h. I look at different redshifts. So the first thing we can see here, if I fix my physical scale and I now basically let time evolve, we can see the matter distribution gets more and more non-Gaussian, right? In particular, the peak wanders to lower densities, right? And I also increase this high density tail here. Right, and what is interesting with this large deviation statistics approach, essentially the idea is if you tell me what's the variance, right, or a theory tells me what is the variance, I am able to predict this shape here, right? That is quite non-Gaussian. So the solid lines are theoretical predictions from large deviation statistics with the correct variance as an input. And the dashed lines are the phenomenological log normal model, right? So you can basically see the log normal is close to correct, but especially at low redshifts, right, it's not quite good enough. And it's also a bit unsatisfactory because there it's not so clear how the cosmology dependence would look like. Of course, we also want more. So although it's called large deviation statistics, in principle, it's sort of accurate in the kind of 2 sigma region around the peak, right? If you go deeply into the tails, there are lots of reasons why this shouldn't work. So Jed in Munich is working on trying to unlock the tails of the probability distribution with SBI. Right. So let's go to the problems, right? So matter is all beautiful, and I think we have a quite solid theory, but once you go to observables, right, it becomes more difficult. So let's imagine we want to do galaxy clustering, right? Roughly speaking, we have the dark matter here, and now we have some tracers. Let's start with spectroscopic tracers. There are two main challenges. So first of all, I could say, okay, if I want to predict a one-point probability distribution, I could say, well, if I have matter and tracers, I first want the joint probability distribution, right, at one point. And then I can basically use my prediction for the matter and get the prediction for just the tracers. And I can reframe this by basically saying, if I know the matter one-point distribution, on top, I need the conditional probability of finding a given tracer density. So here I used halos, given a matter density. And since I'm interested in this one-point distribution at a given physical scale, I basically pick a smoothing scale, right? And if I have a simulation, I can essentially measure this conditional distribution. It's a bit similar to what Jens was telling you about, but this is here in the final conditions, right, in Eulerian space. Right, so this is for halos and the Quixote simulations, and you can see two things. First of all, the good news is if you know the matter density, and I think this here is 20 or 25 megaparsec at redshift 0, if you know the matter density in a cell, right, the average one, you will also roughly know the tracer density. So there's a clear trend here, right? So the black line is the conditional mean. Basically, I give you the matter density and the mean over all halo densities you can find. So this is good news, right? So if we parameterize this, we have a good chance. But obviously, there's a lot of scatter around here, right? So there's a variance. Even if I fix my matter density, right, this won't exactly predict the halo density. There are lots of other quantities that affect this. And here you can see I basically parameterize this with the conditional variance. And here I just roughly added plus or minus 1 standard deviation. You can kind of see if I know the conditional mean and the variance, I can sort of reconstruct this joint distribution. Right, and now we come to the problems. Here I picked one smoothing scale, right? In principle, for every smoothing scale, I have to redo this, right? And in general, this bias that will be nonlinear, so you can already see here, this is not a straight line. This will be scale dependent. And a priori, there's no guarantee that this shot noise here, the scatter, will be Poissonian, right? So this is a problem. And trust me, this is really true. And so let's quickly look at the bias. So here we have different redshifts. We take all halos in the Quixote simulation. So you can see here, those are nonlinear functions. And actually, it's quite important you get that mean right. And this is where this Gaussian Lagrangian bias came in to save us, right? So whatever Jens told you, it really works. Here we basically translate the Lagrangian bias model to a Eulerian one. And we fit the two parameters. And what is nice, we have 3 different scales here. I just show you one, but we basically managed to fit just 2 parameters across the 3 scales, and it works for all of the 3 scales. So basically, if you use the renormalization, this kind of eradicates the scale dependence, which is extremely nice. And we have halos at 3 different redshifts, and we also have a very simple galaxy sample. So this is the Molino galaxies. This also works. So I think this is extremely nice. So I believe that this Gaussian Lagrangian bias can solve problems probably at the field level too, because they make the 1 point nicer, right? Then there's hope for all the rest too. Right, so now I will tell you all of the headache with the shot noise, right? So for me, shot noise literally just means I measure the conditional variance at my fixed scale, and I divide it by the conditional mean. If it's a Poisson, this should be 1, right? So this would be this line. You can see whatever I look at, first of all, it's not 1. It's not even constant. It has a density dependence, and this can be quite complex, right? So you can see here, generically, in particular, the halos can have linear terms, can have quadratic terms, right? And this is quite hard to parameterize. So here we just wrote down a quadratic model for this ratio, right? And we basically fit the same parameters across 3 scales. And this is already where you can see, because we just fit 3 parameters across 3 scales, right? The fit is actually not great. So obviously I could do a better job if I just fit this scale individually here, but then I will have more and more parameters. So I think this is a clear problem we will need to solve. And if you have ideas about this, please do let me know. But the nice thing is, if you have reasonable models for the conditional mean and the conditional variance, you can basically lift your theoretical predictions right from the matter to the tracer. So this is work of my PhD student, Beth, right? Here are shown halo one-point distributions at scale of 25 megaparsec at 3 different redshifts, right? And this is the combined theory model here. So this actually works nicely. Right. You might also ask, can you apply something like this to data? We haven't done it yet because, as I told you, there's lots of headache we're trying to solve. But there was a very simplified theory application to SDSS, where they basically have a very simplified meta PDF model, a linear bias, and some trick to map from real to redshift space by Andrew Rapp and Sapudi in 2020, right? So in principle, that's doable. Right, what else can you do? If you really hate one-point statistics, you can also use insights from this to basically do density-dependent clustering, right? So you can basically split your samples in terms of different density regions. And we basically know that essentially means I can look at the joint distribution of densities at different locations, compare them to the marginals, and at first order, you can basically say, of course, I have an average correlation that is set by the meta-correlation function, and then I have a modulation of the clustering depending on the local density, right? So basically, higher densities are more clustered, lower densities are also more clustered with respect to each other. And you can use this for predictions of density split correlation functions here. Those are actually in redshift space. So this is work by Mathilde Pignon, who's just finishing her PhD at Saclay. And you can see if you stay on, large enough scales, I guess I would say 30 to 40 megaparsec here, it's actually quite nice, right? So the predictions here also Gaussian bias. So this is Gaussian Lagrangian bias too. You can actually see, you can quite nicely predict the difference between high and low densities. And you can see the non-Gaussianity here by the fact that it's not symmetric, right? So I think this is quite promising and we could learn a lot. And there was already an application, an SBI-based analysis of Boss CMAS by Enrique Payas, where they pushed down to even smaller scales than you could hope for this. But I think this is quite interesting. Okay, in the interest of time, let me maybe skip the next thing, but we're also working on different tracers, in particular intensity mapping, like H1, as you could probe with SKA. Actually, the theory model works quite nicely, so this is what my postdoc Bernhard is working on too. Right, but let me switch gears a bit. So I started working on galaxy clustering, right? Being like, oh, this is nice, 3D, but then you have all the problems of galaxy bias, stochasticity, so I got a bit upset and I was like, maybe I want to do weak lensing now, right? Probe the actual matter. Maybe this will be easier. So, of course, the rough idea is, right, if I measure my shears of the background galaxies, essentially I get a way to probe the projected matter distribution. And now I can play the same game, right? I can look at 1-point statistics, 2-point statistics, or any other higher order weak lensing statistic. So my postdoc Lina worked on predictions for the weak lensing convergence PDF. So roughly speaking, the convergence, right, is the projected matter density, and you can get it from the shear by doing a mass mapping procedure here. So Lina lifted previous predictions, including from Alexandre and Sandrine, to tomography here. So here we have several tomographic bins that basically allow you to slice a bit more which densities you actually probe, right, along the line of sight. And in short, the theory model works. But you can immediately think, oh, there's lots of headaches you have to solve for weak lensing too. So just a couple of challenges. The first one is, fact is we cannot measure the convergence directly, right? We measure shear and we basically have to invert the process to get the kappa maps. So here we predicted what is the impact of doing a Kaiser-Squires reconstruction. And this is quite important. In particular, if you're going to have masks, right, you have to be careful because mixing in zeros, well, right, will basically change your signal. We also implemented a simple model for intrinsic alignment. So it turns out for nonlinear alignment model, you can actually just write down how this looks like. And you can also include variance. And if you're interested in this, do ask me about it. Right. And now you might say, okay, 1-point statistics seem a bit boring. What about other higher order weak lensing statistics? And this is what we did in Euclid. So this was the simple case. There was no tomography here. And we compared different beyond 2-point statistics. And roughly speaking, you can see that most of them capture similar kinds of information. So here we have the kappa PDF. We have peaks, Minkowski functionals, Betti numbers, scattering transform, persistent Betti numbers, and persistent heat maps. There are also the aperture mass moments that Laila already told you about. They are only grayed out here because this is a Fisher forecast, right? So if you have non-Gaussian likelihoods, this will make this tricky. So this is why they're grayed out here. But I think this tells you, right, that with 1-point stuff, we can already capture some of the information. Of course, if you go to tomography, stuff will become more interesting. So stay tuned for the follow-up paper. Right, I will skip the covariance, but if you're worried about covariances of 1 point is related to 2-point stuff, and they're still tractable. And what I'm very excited about is that you can do joint statistics. So we just put out a paper that's basically doing joint weak lensing and photometric clustering, right? Which basically means we now can jointly constrain galaxy bias and cosmology. So I think this is the way forward. So I will leave my takeaway here and looking forward to some questions.
Thank you, Cora.